All right, so we started talking about Unit 4 and apportionment and giving out seats is the main focus that we talk about. And so today we're going to actually start the first method, which is Hamilton's method after Alexander Hamilton. And Hamilton's method basically says that every state will get at least its lower quota. Okay. Every state, Hamilton felt like, should get at least their lower quota. Okay. And that's what Hamilton's method says. All right, so let's look at our little example here. So we got 1, 2, 3, 4, 5, 6 states, 6 nations, and we have 250 seats to give out. Okay. And so the first thing is basically what we've done, what we did back in the first section is let's find our standard divider, which is going to be the total population divided by that 250. So it's 50 people each for one seat. And then we found our standard quota. And so here was my standard quota. We did that divided by the 250, and we got here. Now, these are all from example 1. All right. And so the first thing we're going to do, like it said, was we are going to give everybody its lower quota. And we did this in the first lesson. So what's my lower quota? This would be 32, 138, 3, 41, 13, 19. And that's going to be a total of 32 plus 138 plus 3 plus 41 plus 13 plus 19 gives me a total of 246. Okay. So we find our standard divisor, we find the standard quota, and then we give everyone the lower quota. Okay. And that gets me up to 246. So do we have a surplus? Yes. After we've given out everything, we have 4 seats would be my surplus. Okay. We have a surplus of 4 seats because we have 250 seats. We've given out 246 seats. So there's 4 seats left over. All right. So basically what Hamilton's method says is to now just look at the decimal pieces. So if you think about it, the quota decimal part, now this is just going back to the original problem here, was 0.92. This was 0.72. This is 0.08. This is 0.82. This is 0.70. This is 0.76. Okay. And what it says to do by Hamilton's method is the largest decimal piece should get a seat. Okay. And we have 4 to give out. So who are we going to start with? Well, 0.92 would get a seat because that's the largest. All right. And then they're gone. Who else? 0.82 is the next one in line. So they're going to get a seat. And they're done. All right. We got 0.72, 0.70. So 0.76 would be next in line. And we got one more to give out. Well, 0.72 is bigger than 0.70. So they're going to get that 4th and final seat. All right. So what's my final apportionment? 32 plus the 1. So they're going to get 33 seats. They're going to get 139 seats. They're just going to keep the 3. They're going to get 42, 13, and they're going to get 20. And that should be for a grand total of 250 seats. Okay. All right. That's what we call the Hamilton method. And you could ask yourself, going back to what we did in the last chapter, is remember, it's all about whether we feel like something is fair or not. And at first glance, Hamilton's method appears to be quite fair. However, a careful look sometimes will hint that that might not be the case. Compare the fates of State B, or was it State B had 0.72 and State E had 0.70. State B got the last seat. State E got nothing, even though they're only 0.02 of a point away. Sure enough, 0.72 is more than 0.70. So the following rule, we give B the seat and E does not get anything. But it talks about, by the same token though, B is a huge state. And as a percentage of its population, 0.72 represents an insignificant amount. Whereas State E was a relatively small state, and so 0.7 represented 5% of its population. Okay? So when it came to percentages, even though this was a lower number, 0.7, it represented a bigger percentage of the state than did, let's say, State B, being a much larger state. So there are some discrepancies with with the Hamilton method, and we'll talk about those as we go further in this lesson. But those are just some things to talk about. So when we get down here, it asks, Hamilton's method is not population neutral. It is biased in favor of larger than smaller states. Okay, so if somebody asks, are they getting their fair share, then it really is going to depend. But the Hamilton method is not population neutral. All right. So let us take a look at example 2 here. And we're just going to do the same thing. We're going to do, they want us to apportion it by the Hamilton method. They've done our work for us here. They've given us our standard quota. So that just saves us a few steps. So once again, once we find the standard quota, step 2, apportion out the lower quota. So we get 8, 4, 9, 11, 16. And then we ask ourselves, if we add all those together, 8 plus 4 plus 9 plus 11 plus 16 turns out to be 48. So we have two seats left over. So then if you look at just the decimal pieces, all right, they are definitely going to get one. And even though these are all close, 0.388 wins out, they get the other one. So what's my final apportionment? 8, 4, 10, 11, 17. That should be my 50 seats. Okay? So that's what we call the Hamilton method. All right. So now you have example 3. All right. I'm going to pause for a second, or you might need to pause for a second and take a second and see if you can solve this whole problem using Hamilton's method. So take a pause and then see what you can do. All right, so you should be done, and you're just going to be checking yourself, but our total here was 2,200. So we need to find our standard divisor. So 2,200 out of, there were 150 seats. So 14.3 or 66 repeating people for one seat. Okay. And then we found our standard quota by doing what? we're going to do that 300 divided by 14 and 2/3, and that turned out to be 20.45. 20.45. So 450 divided by 14.6 repeating turned out to be 30.681. 800 divided by the standard divisor turned out to be 54.54. 650 divided by was 44.318. Give them the lower quota, 20, 30, 54, 44, 20, 30, 54, 44. That's 148. There's 150 seats. There's 2. So if I look at my decimals, this was 0.4, 0.6, 0.5, 0.3. So they should get 1, and they should get 1. So if I add, so that'd be plus 1, plus 1. So I got 20, 31, 55, and 44 for a total of 150. All right, questions. All right, same thing down here on number 4. If you want to hit pause and see what you can do first, then do that. But here's what we got. And they want us to give out teaching positions. So take a minute, see what you can do, and we'll see you here to check yourself. All right, so you should have this done. So now you're just checking yourself. I added all these together and got 1540. Okay. Now it's a little bit off the page there, but added them all together, got 1540. And then I divided it by the 40 positions. And so we got 38.5. Okay, was my standard divisor. So then if I divide all these by 38.5, if it helps for you to add your little table in there like we've been doing, you could do that. So this was 7.11, 9.66, 8.59, 7.89, and 6.72. All right, give everybody their lower quota. So 7, 9, 8, 7, 6. 7 plus 9 plus 8 plus 7 plus 6 is 37. We had 40 teaching positions. So now we're going to look at our decimal parts. And 0.1, 0.6, 0.59, 0.89, 0.72. And so we need to give out 3 more to get to our 40. So 0.8 is the largest. 0.7 would come next. And then 0.6 would come next. So those 3 get the 3 extra surplus seats. So my final is going to be 7, 10, 8, 8, and 7. Okay. All right. And so the last thing we need to talk about, once again, kind of tying into the last chapter, is the fairness criteria. And the first rule we're going to talk about is what we call the quota rule. And it basically just states that a state should be apportioned a number of seats, shouldn't be apportioned a number of seats smaller than its lower quota or larger than its upper quota. So if you think about it, the Hamilton method satisfies this. We will never get lower than our, and then less and more. So we will never get less than the lower quota or more than the upper quota. All right, so